Hey, good morning, everybody, and thank you for joining us. Here we are, it's Friday morning. We are here with the Future Panther Academy. My name is Bonnie Pugiasco. I serve as the Special Events Manager for the Alumni Association at the University of Wisconsin-Milwaukee. So here we are presenting the 7th program in our 9-week Friday morning series called Stars Have Stories. Hasn't it gone fast? Hey, if any of you have missed our previous 6 programs, you can go to the UWM Alumni Association website. Look at the links. You can watch any of them on demand anytime you want. So good thing to know, catch up on those. Meanwhile, today, our program, Stars Have Stories, is the special episode called How Are Stars Born? And once again, we have Dr. Jean Creighton with us. She is an astronomer and the director of our planetarium at the University of Wisconsin since 2007. So if you folks are watching live right now as we're broadcasting this Friday morning, don't forget you can send your questions to Dr. Jean using that little chat box, and we'll get to as many of those questions as we can at the end of the program. So everybody settle in. We've got a great program for you today. Again, it's called How Are Stars Born?
Well, I'm so glad that you're here to talk about one of my very favorite subjects in the whole world. How are stars born starts with, are they born? Because for a long time, people looked up, they saw stars night after night after night, and they assumed that they all have always been there. They didn't start and end. They're always like good friends you can count on. They're always there for you. And here is the thing, we had a surprise. So let me show you a star field that's a pretty typical star field. And notice how the stars look kind of blobby because we've really zoomed into this star field. And you won't see it right now because it's very, very dim, but there's something there in that regular star field kind of in the center that hasn't happened yet. So here's a star field and we think, okay, there's Bob, there's Ann, there are all these friends that we have, right? Stars are like friends. And then we wait for another few nights and we look at that same field and we start seeing a star there that we hadn't noticed before. And we think, look at that, there's something new there. That's weird. And the following day, what's that? Oh my goodness. We started noticing that stars sometimes just appear. This is a nova, as it turns out, and I don't want to spend the time explaining what a nova is, but I'll just tell you it is the Latin word for new. This is a new star, and you might have heard the word nova in supernova. That's an even brighter nova. So this is something that a star that wasn't there all of a sudden wakes up, makes this amazing appearance, and then you wait a few days, we're back to normal. That star becomes really quiet again. This tells us that in fact, stars do change. Stars are not always the same. Stars might have a beginning and an end. This is a big deal, big philosophical change from what we thought for thousands of years. All right, so then you might ask, okay, so stars change, maybe they are even born, maybe they die. Where does that happen? How does that happen? So the question became, well, is there material between stars? Is there stuff between stars that might give birth to stars in time? And that's not an easy question to answer because if you look up, you see a star, you see another star, and most of the rest of it looks kind of dark, right? Looks dark. There are exceptions to this. There are places in the sky where you can see there is stuff. Let me show you probably the most famous example of that in the constellation of Orion. the three stars in the top are what we often call the belt, right? And then from the middle of the belt, from the buckle, if you will, there is a sequence of stars that almost look like what I call a sword. In the middle of the sword, there's this beautiful, you see it almost as a pinkish white, that is a cloud, a nebula. Nebula is the Latin term for cloud. And that is probably the most studied star forming region of all. In that cloud, as it turns out, there are stars born right now. But I'm showing you this picture just to show that there are places where it looks fuzzy, not star-like, but there are areas where we do have stuff between stars. Okay, that's one example. The other example I want to show you is called the Coal-Sack Nebula. Now, pay attention to this picture. There's chock-a-block stars all over the place, all over this picture. But in the middle, it almost looks like there are no stars at all. And you could imagine maybe that, well, yeah, maybe there are really, really no stars there. But how could you think that, considering that there's so many stars all around? What we eventually realized is that there's a cloud in front of us, between us and the stars. So where it's absolutely dark, that means the cloud is densest and no starlight from behind it gets to us. You also perhaps notice that at the edges of the cloud, it gets a little less dark. So stars start making an appearance. They're not as bright as they are at the edges of the image, but they're starting to creep up on us. Do you see that? So that would be another suggestion that there is stuff in the interstellar medium. That's the fancy word, by the way. If you want to talk about the stuff between stars, you say inter, between, stellar, stars, medium, interstellar medium. That's a fancy word for today. Notice also the scale, right? This cloud is 50 light years across. Think about that. A cloud that's 50 light years across. So that would be an example. Next, let's go to another way we know they're clouds. Now, look at this. This is the Orion constellation, right? I've talked about before how it looks a bit like a bow tie, and in this case, it would be a standing up bow tie. I showed you before the Orion Nebula. This is a visible image. In other words, I took a camera, I attached it to maybe something like a pair of binoculars or a pretty modest telescope, and this is what I see. Other than the Orion Nebula, do you see any other stuff between stars? Or does it look mostly, all I've got here is stars? Let you think about that for a sec. Because I'd say, obviously the green lines we added with Photoshop, right? But I'd say everything else pretty much, except that one little blob I see there in Orion's sword, looks like a star to me. And that's because I'm not using the right glasses. If I change my usual glasses and put on infrared glasses, that's a different kind of light, then what I see changes. Let's see with infrared glasses. Wow. I can barely see any stars here. Now I see the clouds and the dust, the huge amount of clouds that are in the same region that are giving birth to stars. So where it's super bright is where it's hot, and that's where young stars are forming. Isn't that mind-blowing? That you can completely change what the sky looks like with different kinds of lenses. And that's why in astronomy we look at so many different kinds of light, because it gives us insight what's really there. Otherwise, we just don't have the whole story. Now we see, oh, we've got a huge cloud that is capable of giving birth to stars. And now we'll have a chance to, in a minute, to kind of talk about how that really happens. So to recap, what we've established is that stars change. They're not always the same. They have a beginning, they have an end. We also found that we have nurseries of stars in what we call the interstellar medium, and specifically, we have them in clouds of gas and dust. So we'll walk together that process. How does that work? We should say that these clouds, a lot of the time, are just sitting there. I have a blob. This is my stand-in for a cloud. And a lot of the time it's just sitting there. And it's sitting there happily because there's a balance between two forces. We have two things fighting in a star, both early on before it even forms, all the way to later on in its career. So we have gravity on one side. We'll get to that in just a sec. We have gravity in one side, and we have internal pressure on the other. And these two things are constantly fighting. The reason why I have a picture of me here, two pictures in fact, is because the question of how are stars born is something that I've been curious about all my life, as long as I remember myself. This is a picture of me when I'm about 5. And apparently I was walking down the street with my mom, and I looked up and I said, "Mommy, how are stars formed? How are stars born?" And it's, I think, nice and fun that that's one of the questions that's kind of driven my career for a long time. The other picture is me standing on Mauna Kea. That's the big island of Hawaii. That's a volcano, happily not an active one right now. I'm standing at 9,000 feet at the level where astronomers had their quarters to sleep, because I was observing star forming regions of another galaxy with one of the big telescopes on the summit of Mauna Kea. So it's nice to see that one of my questions as a kid has been something that I wrote a thesis about in another galaxy. Think about that. So you could be one of those people, right? You could continue to ask the questions of how we form stars. It's a complicated enough question. There's enough research for everyone. Just saying. Okay, so I'll get back to how stars' career changes based on this struggle. Gravity wants, and you can use, please, I encourage you to use your hands with me. Gravity is pushing a star to shrink. That's what it's trying to do. And the internal pressure says, no, I do not want to be squeezed any further. Stop. In fact, I'm going to expand this star. And this balance is what determines what the star is going to do next, because the star can expand if internal pressure is winning. It can contract, it can shrink as if gravity is winning. So for a long time, my cloud has a balance between the internal pressure and gravity, and it sits there sometimes for hundreds of thousands of years, until a nearby star goes supernova. And we've talked about that in previous programs. Sometimes stars, the very massive ones, explode. And that explosion makes very fast winds, faster than the speed of sound. Almost the speed of light, not quite, but very fast winds. So these winds, they hit the cloud, and that gives gravity a little bit of a boost. So the cloud starts collapsing, starts contracting, and that gives gravity a real help, because now as the star gets denser, gravity becomes stronger, and the various regions in the cloud start shrinking, start collapsing within, and each of those areas can make a star in principle. As they start shrinking, they get warmer. So let's look at an artist's impression of what that cloud looks like. At first, it'll be just a little warm, right? So that those particles start getting closer together. They start, they translate some of that gravity into heat. And as time goes on, our cloud is going to get warmer. And eventually, it has what it takes to make a star. And let me remind you what that is, because some of you might not have been there when I talked about what makes a star, and some of you might need a reminder. To make a star, I need to be so dense. The cloud needs to be so dense that I can take protons, in other words, the cores of hydrogen, slam them together. So I have little protons. Those are very small particles in our atoms. Slam them together, make helium a heavier element with 2 protons, 2 neutrons. And that process releases a huge amount of energy. And it's so efficient that a small fraction of the mass of the sun is going to keep it shining for all its life, for 10 billion years. So the moment the cloud gets dense enough and hot enough in its core to allow what we call fusion, that's when the star turns on. And you still have leftover material. Right here was our cloud, and we can see a real picture now. This is a real image of the inside of the Orion Nebula. We see several of these baby stars. They've turned on. So, but there's still quite a bit of stuff around them, still a lot of the original cloud. And that cloud material is going to make planets. Now, you can think of it as, imagine the nebula is like pizza dough, right? We start with a blob of pizza dough. And the pizza dough is twirling. So slowly it's going to make a disc, right? Like a CD. And most of the material in our pizza dough is going to make star, right? But some of it is going to be left over, like planet material. So the leftovers, the scraps, if you will, are going to make the planets around the star. This is our idea. This is what we thought for many years, but we didn't have clear proof. Our computer models told us it has to work this way. But let me show you a real image that we were able to take of a very young star forming planets around it. Check this out. This is a real image. The star has formed in the middle, right? This is turned on. There's still plenty of material leftovers that slowly are going to form planets. You see places where it's a little brighter. That's where there's more material around the star. And you see already that in some places, the material has been cleared out, because as the planet forms, material is attracted toward it and it clears up its own path. And eventually you get a completely cleared out solar system. You have the star, you have your planets, and nothing else. So like our solar system today, we don't see remnants much of that cloud, because the light of the sun is so powerful and it's been shining for so long, it's swept up most of the debris, and all you're left with is a star and planets. So today, not only did we make stars, we also made planets around other stars, which blows your mind if you think about it, because that means that there could be people like us talking about the birth of stars somewhere else. And maybe with that, I'd be delighted, as always, to talk with you about any questions that you might have.
Okay. All right. So here we go. Our first question is from Candace. and she would like to know, how long does it take for a star to be born?
Great question, Candace. It depends. The very massive stars form relatively quickly, so a few million years. The low mass stars take typically longer, so that could be many tens of millions of years. But usually stars are formed on the order of hundreds of thousands. I'm going to correct myself because I think I spoke quickly and I was thinking about the age of the star. Talking just about its formation, you would be looking at tens of thousands of years to maybe hundreds of thousands of years, maybe even a million or so, depending on the mass. So the smaller the star, the longer it takes to get with the program, and the more massive it is, the faster it does, which is maybe a little odd, but that's how it works. Great question.
All right. Thank you. All right. And our next question comes from Dora. Dora wants to know, where in the galaxy are most stars born?
Great. This is another great question. If you imagine our galaxy like also a CD disc, so here I've got, let me show you a galaxy. A galaxy is like a sheet of paper. I don't have a round sheet of paper, but this would be what we call the disk. Okay. Now the galaxy also has stuff, we call it the halo, but it's much, much, much less stuff than there is on the disk. So it's the disk that produces the vast majority of stars. That's where we get most of the star formation. And indeed, when you look at pictures of galaxies where you see really bright reddish areas, that's where the action is. Great question.
All right, and our next question comes from Alex, and he would like to know, how does the process of a star being born even start?
Yeah, so that's where I talked about a cloud that's sitting here, and it gets hit by some kind of shock. That's the term we use, a shock. So a disturbance that travels through space that hits it so fast that it really, well, it doesn't know what to do. It kind of collapses from the hit. I like to say that stars recycle. The death of one star, right? The explosion of one star is the kind of impetus, is the excuse for another whole generation of stars to form. So that's a nice idea that even stars recycle. Great question.
That's a great question. And our next question comes from Lara. What determines how much energy and matter a star needs to be born?
That's another very good question. I didn't talk about this in any detail. We need a minimum amount of temperature and density to encourage protons to fuse together. If it's not hot enough, so it needs to be several million degrees before protons can come together. So it's not so important how much matter you have. The real question is, how successful were you in squeezing it to a small enough volume that you can start fusion? That's what determines it. So if I get a high temperature and high density, that's when I've got just the right conditions to start formation of a star.
Okay. And our next question is from Anna. What is the nebula called in Orion's belt?
We had this question earlier, so I was able to look up all the names of the Orion Nebula because I wouldn't have had this handy. Often the nebula is called simply Orion's Nebula. It is, after all, as I mentioned, the most common, the most observed star-forming region. However, it goes by other names too. It's also known as M42. It is, in other words, the 42nd entry in the Messier catalog. I'll have to look the other ones up. NGC is the New General Catalog, and it's 1976 in that catalog. It's in the Sharp List 281. So in case you're wondering, what, doesn't it have just one name? Why are you telling me all these names? We have multiple names for things sometimes because they appear in different catalogs. And it's nice to have all those names because then you can look, you can do a search and find all the information that we know for this particular nebula. It is a large nebula. Many, many, many papers have been written for this particular region in the sky. Great question.
All right, our next question is from Sydney. Do you know how far away Orion's nebula is from Earth?
The honest answer is no, not offhand. But if I had to guess, that's something easy you can search with a parent. But my guess would be it's a few hundred light years away. That would be my guess.
Okay. And our next question and final question this morning, Jake wants to know, do stars have parents?
Stars don't have parents quite the way that you and I do, but they are born in clouds. So we sometimes talk about a parent cloud. And by the way, these clouds don't just make one star. They often have twins or triplets or even more. They make groups, they give birth to groups of stars together. And we suspect that the sun might have had a twin, but because star formation can be pretty violent, lots of fast winds are produced. It could be that twin got kicked away and now we're separated. But yes, so clouds give birth. Clouds are parents to stars. Great, fun. So thank you so much for engaging with me and thinking about how stars come to be. Next week, I look forward to telling you some stars. I am an astronomer, but I love myths. I grew up in Greece. We're not going to only talk about Greek myths, since everybody on the planet had stories that they associated with constellations. They saw patterns in the sky. So I look forward to sharing some of my favorite stories with you next week. Thanks so much.